Hello friends, welcome back. In this section, we are going to continue our discussion of virtual port channels, and in specific, we will be discussing about some of the VPC failure scenarios that we can run into in a VPC domain. We will also discuss some of the negative impacts of these failures that we can have in our network and some of the ways to solve these issues from a design point of view. So as discussed previously, in a VPC setup, there are two devices that act as VPC peers. One of them is the VPC primary and the other one is the VPC secondary. The goal of the feature is to take a physical triangle topology and logically represent it as a point-to-point topology. But the potential problem with this design is that the upstream switches, they have their own independent control planes. And in certain failure scenarios, we can run into an active-active or a split brain situation where the control plane between the VPC primary and VPC secondary is broken. When this happens, the secondary may assume the VPC primary role while the original primary maintains its primary role, which might result in forwarding conflicts in the data plane. To prevent this, we can use the VPC peer-keepalive and the VPC peer-link. As discussed previously, the VPC peer-keepalive is a UDP ping that runs back and forth between the VPC primary and the VPC secondary to verify that both peers are active. The VPC peer-link, on the other hand, is used to synchronize control plane information such as the MAC address table, the op cache, and other consistency parameters. And this is exchanged over the VPC peer link using a protocol called the Cisco Fabric Services over Ethernet, or CFSoE. Under normal conditions, when the peer link fails, the VPC secondary device suspends its local VPC member ports and any SVIs associated with VPC VLAN instances. So for any VLANs that is running across the VPC peer link, the secondary device will suspend those SVIs. The reason being, the secondary cannot determine if the primary peer is still active. It only knows that the control plane communication is lost. So to prevent loop in the forwarding plane or the data plane, the VPC secondary shuts down its local VPC ports and allows the VPC primary to continue forwarding traffic as normal. This will prevent the two VPC peers getting into an active-active state, and it is the desired behavior. However, this can impact orphan ports that are single attached to VPC secondary's SVI as its default gateway. The best practice is to avoid orphan ports entirely. So each downstream device should be dual attached to both the VPC peers, and if single attached devices must exist in the network, they should reside or connected in completely separate VLANs that do not traverse the VPC peer link. So in the failure chain of events, if only the VPC peer-keepalive fails, the VPC itself stays up because the peer link is still active. The VPC peer-keepalive is a backup mechanism to detect peer failure and prevent split brain if VPC peer link goes down. On the other hand, if the VPC peer link goes down first and then the keepalive fails, that's when split brain can occur. So continuing our discussion around the chain of events that follow when the VPC peer link goes down, the failure detection in a VPC domain relies on certain timers. So when the peer link goes down, the secondary waits for the keepalive timer and the hold timeout to expire. If during this wait it receives a keepalive from the primary, it disables its member ports and stops forwarding traffic. So it effectively removes itself from the VPC domain. So going back to our topology, we have the two VPC peers, peer 1 and peer 2, connected over peer 1 as its VPC peer link, and they're also connected via management interface for the VPC peer-keepalive connectivity. So in our topology, peer 1 is the primary device and peer 2 is the secondary device. So now if the VPC peer link goes down, the peer 2 will shut down its VPC member ports connected downstream, and it will also suspend its SVIs for any VLANs the VPC peer link. So if we check these timers on the CLI and run the command show VPC peer-keepalive on any of the two VPC peers, we see that the timers are 5 seconds for the peer-keepalive and 3 seconds for the hold timeout. So after 8 seconds, if the VPC secondary still does not receive a keep alive from the primary peer, it will shut down its VPC member ports and suspend any SVIs for the VPC VLANs running across the peer link. So after the hold timeout expires, if the VPC secondary device does not receive any keep alive from the primary, it will assume the primary role and continue forwarding traffic. But if a keep alive is received, the secondary device will suspend VPC member ports. So the VPC secondary device is now effectively non-operational. So what happens now if the primary peer fails completely? So we have the secondary device which has already shut down its member ports and the SVIs. And now we have the primary device which has failed as well. So in this case, the VPC secondary device will not bring up its VPC member ports and the SVIs. The reason being, the VPC secondary device does not continually check for the VPC primary device availability. So there is no keep alive or heartbeat mechanism that runs back and forth between the VPC primary and VPC secondary device, with the final result being that both the VPC primary and secondary peers are now effectively out of path. So to recap, the VPC secondary device, upon peer link failure, shuts down its member ports and suspends its SVIs. The VPC primary now completely fails. The member ports and the SVIs on the secondary still stay down. To solve this failure condition, Cisco came up with a feature called VPC Auto Recovery. It's a feature that is disabled by default, and it allows the secondary to assume the primary role if it detects that the peer has gone down after a peer link failure. So let's assume that the VPC peer link has gone down. The secondary will wait for the timers, i.e. the keep alive timeout and the hold timeout to expire. If in this time, if the secondary still receives the keep alive, it will suspend the VPC member ports like we discussed. But now if the VPC primary goes down, with the auto recovery feature, VPC secondary will now actively check for the primary device, and it will promote itself as the VPC primary, and it will enable its VPC member ports. And now if the VPC primary recovers, it will stay as secondary as there is no preemption, and it will save the devices to go through a convergence event. And another instance where the VPC auto recovery feature can help us is when there is a power outage on both the primary and secondary VPC peers. Without auto recovery, once the VPC peers have rebooted and the VPC peer link remains down, neither switch can determine its VPC role, as the VPC role election occurs over the VPC peer link. And since there is no role election, the VPC member ports will never come up. Like we discussed in the first section, there is a dependency between the VPC ports, the VPC peer link, and the VPC peer keep alive. So the VPC member ports cannot come up if the VPC peer link is down, and the VPC peer link cannot come up if the VPC peer keep alive is down. However, auto recovery changes this behavior, as it allows a single VPC peer to elect itself as the VPC primary after configured timeout has expired if the VPC peer link never comes up after reboot. the timeout period, the peers will wait before promoting itself as the primary device is 240 seconds. That's the default timeout. However, auto recovery also comes with its own level of risks. For example, if both the peer link and the peer keep alive fail simultaneously while both devices are operational, each device will believe that the other one is down and both will promote themselves to primary, resulting in a split brain condition where both devices will start forwarding traffic independently, causing serious network disruption. So if we have a break in the peer keep alive and the peer link at the same time, then both peer 1 and peer 2 will assume the primary role, resulting in a split brain scenario, and they will both start forwarding traffic independently. To minimize this risk, it is recommended to have redundant supervisors, power supplies, physical links, line cards on these Nexus switches so that the probability of simultaneous failures remains quite low. So worst case scenario, we can turn off the feature VPC on the secondary device so the devices fall back to spanning tree. So in summary, we should ensure that the devices have ample redundancy and we avoid orphan ports. So with proper planning, we can prevent split brain scenarios and ensure consistent traffic forwarding in the network. So now let's go to the CLI and simulate a VPC failure scenario so that we have a better understanding of the failure condition. So this is our VPC topology that we will be working on. So we have VPC established between peer 1 and peer 2. If we do a show VPC, we have the peer keep alive, which is alive, and peer adjacency formed OK. And we are using port channel 1 as the VPC peer link. So in our setup, we have the VPC peers peer 1 and peer 2 in our VPC domain, and these ports going downstream to the servers are in our VPC. So we have the ports going down to server 1 in VPC 10 and the ports going down to server 2 in VPC 20 from the VPC peers point of view. And from the server's point of view, these ports are configured as part of port channel 1 towards the upstream switches. So now let's check the VPC state on peer 1 and peer 2. So let's do a show VPC. So we have the peer keep alive, which says peer is alive, and for peer status we have the peer adjacency formed OK. And towards the servers we've got the port channel 10 and 20 going downstream, and we have exactly the same state on VPC peer 2. So now if we have to simulate a peer link failure, so let's bring down the peer link on peer 1. So if we say interface peer 1 shut, and in our topology, peer 1 is a secondary device. So what we should see is that peer 1, which is the secondary device, will bring down its VPC member ports. So we have the peer link that has gone down, and then if we check the status of the downstream port channels, the secondary device, which is peer 1, has brought down its downstream member ports, and the reason being the peer link is down. However, from the VPC primary perspective, the VPCs are still up, and if we check the traffic flow between server 1 and server 2, and let's confirm the IP addresses on these devices. So on server 1, we've got an SVI for VLAN 10 with an IP of 10.10.1.1, and on server 2 we have SVI for VLAN 10 with an IP of 10.10.1.2. So if we simulate traffic flow between these servers and ping server 2 from server 1, we see that the servers can still ping each other. And if we check the port channel status on these servers, we should see that the link towards the secondary device, which is ETH11, or the link going towards VPC peer 1, is currently suspended. And let's do the same verification on server 2. Yeah, we see the link towards VPC peer 2 in suspended state. So we brought the VPC peer link backup on peer 1. So peer 1 is backup. It is the VPC secondary device. So now let's simulate a complete failure of the VPC primary device after the VPC peer link goes down. So on peer 1, which is our secondary device, we will bring down the VPC peer link once again. So interface peer 1 shut down. So on VPC peer 1, we've got the member ports gone down, the reason being the peer link is down. So now if we reload the peer 2 to simulate a power failure on the VPC primary device. So now when we had a power failure on peer 2, the VPC secondary device did not bring up its peer link. So it still says the port channels are still down, the reason being the peer link is down. The end result being there is a failure in the data forwarding and the servers could not ping each other anymore. So like we saw, when the VPC peer link went down, the VPC secondary, it did shut down all its VPC member ports. And then when there was a complete failure of the VPC primary device, the VPC peer 1, which is our secondary device, did not bring up the VPC member ports, resulting in packet loss or traffic black hole. So now the VPC peer 2 has come back up and it has established the VPC peer link. Like we see, the peer is alive and peer adjacency formed OK. It has also brought up its VPC member ports, port channels 10 and 20. Likewise, the secondary peer has also brought up its VPC member ports, PO 10 and 20. So now if we check the data forwarding between server 1 and server 2, yeah, they are able to ping each other again. To overcome from this failure condition, Cisco has introduced the VPC auto recovery feature like we discussed earlier. It is disabled by default, and to enable this feature, all you have to do is just go to VPC domain config mode. So VPC domain 1 in our topology, and then the command is auto recovery. So this enables auto recovery feature. So likewise, we'll do the same on VPC peer 2. So VPC domain 1 auto recovery. So if we do a show VPC now, we see that the auto recovery status is enabled and the default timeout is 240 seconds. So let's say if we go back to peer 1 and shut down the VPC peer link, interface peer 1 shut down. Let's do a show VPC. The VPC member ports are down again, the reason being the peer link is down. We still have data forwarding between the servers as the ports on the VPC primary device is still up. So now if we have to simulate a complete failure of the VPC primary now, let's do a reload. Yes. So we have initiated the reload on VPC peer 2, which is our primary, and then now we see the status of the keep-alive on peer 1. It says peer is not reachable through peer-keep-alive, and also the VPC peer link is down. With the VPC auto recovery feature, we see that the secondary device has now promoted itself to be the operational primary. And now if we check data forwarding between server 1 and server 2, we see that they are able to ping each other, even though the VPC primary device is still rebooting. So we see the VPC secondary device has promoted itself to be the operational primary. And for the VPC status, it says the VPC type 1 and 2 checks were bypassed for the VPC member ports, as our VPC peer link is down currently. Hence, it is crucial to have physical redundancy in the VPC domain. So like we discussed earlier, we should have redundant supervisors, power supplies, just to ensure that no single failure can cause a split brain scenario. And in general, when initializing VPC, we should configure the peer-keep-alive first, then the peer link, and then the member ports in this particular order. And in a production network, the failure scenarios can get complex. So we should plan the redundancy carefully and know how to recover if multiple failure occurs. In the worst case, we can always disable VPC on one switch so that we don't have VPC running, i.e. with a no feature VPC command to restore connectivity through standard spanning tree forwarding. So friends, in our upcoming sections, we'll go over some of the other VPC features like VPC peer switch and peer gateway. I hope you liked this video. If you did like the content, please hit the like button, share your comment. Any feedbacks, good or bad, is welcome. And please share the video with your friends and colleagues. Also, you can support the channel through Buy Me a Coffee. The link is in the description. So friends, thank you very much for your time today, and I will see you in the next video. Thank you.